The James Webb Space Telescope is challenging some of our most well-established scientific assumptions, providing data that pushes scientists to reconsider traditional cosmological models. Among its most surprising discoveries is the identification of extremely large and massive galaxies in an early phase of the universe, contrary to what was predicted by galactic formation models. This discovery raises fundamental questions. If we have misunderstood the evolution of early galaxies, could we have also misinterpreted the beginning of the universe itself? The Big Bang theory, widely accepted in the 20th century, describes the origin of the universe as an explosive expansion from a singularity, a point of infinite density and zero space-time. According to this theory, space, time, and matter were born from this singularity about 13.8 billion years ago, initiating the expansion of the universe, which continues to this day. However, despite its broad acceptance, the Big Bang theory is facing growing criticism, especially in light of new astronomical discoveries and unresolved theoretical gaps. One of the main critiques concerns the so-called cosmic inflation, a process that supposedly occurred immediately after the Big Bang, during which the universe expanded exponentially in a fraction of a second. Although this theory solves some issues related to the structure and distribution of matter in the cosmos, such as its surprising large-scale uniformity, the mechanism that would have caused inflation remains uncertain, and many physicists consider it an ad hoc solution rather than a definitive explanation. One of the fundamental pieces of evidence supporting the Big Bang is the cosmic microwave background radiation, CMB, a faint microwave radiation that pervades the entire universe. This radiation represents the leftover energy released about 380,000 years after the Big Bang, when the universe was still a glowing mass of plasma. As the universe expanded and cooled, hydrogen atoms formed, allowing light to travel freely through space. The discovery of the CMB in the 1960s was a decisive blow in favor of the Big Bang theory, as its existence had been predicted by the Standard Model. Observing this radiation confirmed the idea that the universe was once much hotter and denser than it is today. However, even with this important confirmation, many open questions remain. For example, the theory cannot accurately explain why the universe is so homogeneous on a large scale, or how exactly matter was distributed in the early stages of expansion. One of the most complex and fascinating questions in modern cosmology is, what existed before the Big Bang? Traditionally, this question is answered by saying that time itself began with the Big Bang, so asking what came before is a meaningless question. Stephen Hawking, for example, compared this question to asking what lies north of the North Pole. Time and space as we know them did not exist before that moment. However, not all scientists accept this view. Some cosmologists suggest that the Big Bang might not have been the absolute beginning of the universe, but rather a transition within an eternal cycle of expansions and contractions. This hypothesis leads to the theory of the Big Bounce, according to which the universe expands to a maximum point, then collapses on itself and bounces into a new phase of expansion. In this model, the Big Bang would not have been the beginning of everything, but just one of many cycles of cosmic birth and death. One of the main obstacles to the Big Bounce theory is the problem of entropy, defined as the measure of disorder in a closed system. According to the second law of thermodynamics, entropy tends to always increase. If the universe goes through infinite cycles of expansion and contraction, entropy should accumulate over time, making each new cycle more disordered than the previous one. Eventually, the universe would become completely chaotic, unable to sustain the formation of galaxies, stars, or even atoms. However, loop quantum gravity theory might provide a solution to this problem. According to this theory, space-time is not continuous but made up of indivisible units called loops, about the size of the Planck length, approximately 10⁻35 meters. This discrete structure of space-time implies that infinite density, as predicted by the Big Bang singularity, is not possible. Instead, gravity at some point reverses, pushing matter away rather than attracting it, preventing a complete collapse into a singularity and leading to a bounce. In this scenario, each cosmic cycle forgets its past, resetting entropy and allowing a new beginning without accumulating the disorder from previous cycles. This would not only solve the entropy problem, but also explain how the universe can continue to exist in an eternal cycle. The possibility of a cyclic universe and the ongoing expansion of our knowledge through tools like the James Webb Telescope open new avenues in understanding the universe. Alternative models like the Big Bounce, supported by emerging theories like loop quantum gravity, are gaining ground, challenging the classical Big Bang model. If these theories prove correct, we may need to radically rethink our concept of time, space, and matter, accepting the idea that the universe may never have had a true beginning, but is rather a cyclical entity in continuous transformation. Thanks for watching. Leave a like, subscribe to the channel, and activate the notification bell so you don't miss the next videos.